5 remains of individuals dated 1.8 billion years were discovered. You know, Georgians are known for self-criticism and for having good sense of humor at the same time. And every time I hear Dmanisi, I recall a story. I don't know how much of truth is there, but I like it. You know, when the president of Georgia by that time was informed that first Europeans, that David Lord Kipainza discovered first Europeans dated 1.8 million years were discovered in Dmanisi, he said, I personally had no doubt that the very first savages were Georgians. But to be serious, I believe the conference aims at developing new approaches in international interdisciplinary research, and I'd like to thank National Museum of Georgia and Zенкенберг Museum for making this conference possible. I'd like to welcome you once again here in Tbilisi and wish you a very fruitful and successful ending of the conference. This is the last day, and we're looking forward to the absolutely fantastic exhibition that is opening Monday, and there was the closed opening, and you had the chance to see the level and the level of the exhibition, the level of the work that the team of the National Museum represents, and honestly speaking, I'm very proud for the National Museum and for all of us. So welcome to Tbilisi again, and thank you very much for participating in the conference. Thank you.
Thank you, Mr. Georgadze. Yeah, I was joking, remember. Before became Minister of Culture, he was running very big company which was famous for bringing very famous musicians in Georgia. And this was first, I remember when first James Brown came, Ray Charles, Herbie Hancock, and I told, he was bringing them separately. I brought all of you together, right? So this was the point. Thank you, Bishop. Good morning. Now, let's go back to Dmanisi and go back to our work. I was thinking yesterday night what I should say after these 25 years. And it came back really many memories, what happened and how the story was developed. And I thought maybe it makes sense to tell you a little bit how we can see Dmanisi and what is for us this project. And then we will try to present you all aspects of work which is actually in progress. You will see our team, which is more like family already. I'm very proud to say that we have different generations, different countries. We have many new young people, and I hope we will have more. And this is a story which starts, you already know, 80 years ago. So Dmanisi, first excavations, we have 25 years of Dmanisi mandible, but at the same time we have 80 years of first excavations. And, we are talking about luck, about chance. You should be lucky to have luck, right? But if you are not moving things, you will never get anything. The luck will stay somewhere, right? So this is, I think, very good example. When you are somewhere luck is hidden and success is hidden, you should be prepared for it. And why I am saying it, that if in our country we would not have tradition of science, I'm not sure that Dmanisi discoveries will happen that way. Maybe it will happen one day. So this was always for us, for Georgians, important to study on history and to have school of researchers. And first excavations in 1936 started by very famous professor Levan Muskhelishvili, was already, may I say, the standard, which was that time science. So since that, we knew what is this medieval city and what should be medieval city as a phenomena. You see, when I mentioned about traditions, most of you, I imagine, already saw these beautiful archaeological items which are in our exhibits on the downstairs. These beautiful items, most of them, 95% were found by systematic archaeological research, and not on the Marché aux Puces or in antiquities. It means that we had this tradition of archaeology. If it will not be, it will be lost, right? So this was for me today to see on the past that how important it is to keep these traditions and continue it. So then I will not bother you, will tell you all stories of Dmanisi, but since 36 and 37, we had research. We knew what is as a historical site, and you will see tomorrow this is a well-planned medieval city which has also connections with trade routes in different parts of the world, and it could be like the Silk Road, one of the part of Silk Road. But that's not our topic. And then what I would stress also importance that there are different versions. I think the main version, what is true, that people were suspicious with bones. Who brought first to Obesalom Wekua, nobody knows, but it's important that he saw it. It was 33 years ago, and he realized that it's a rhino. So still going back, it's a traditions, right? Knowing where are the bones. And then next years, since 84, when a student of archaeology, Nugzar Mgeladze identified stone tools, story started. And I would like really to say many thanks to people who started it. Started Professor Japaridze, who was very dedicated man, historian of medieval history, and who was somebody with a very, very big dedication and enthusiasm of the Paleolithic side. And he passed away exactly after the Dmanisi discovery next year, 92. So this was a prelude, and then were some works like work of excavations of also late Bugianishvili, were some research of geological research. Professor Wekua did quite good identification of fauna. And when we came in 25 years ago to start excavations, I would say it was clear that this is important. What I wanted to say that it's not that we are so genius, came suddenly and opened this beautiful site. Everything was there. Simply, this was a chance to bring new science. And I am very grateful to my German colleagues, particularly Gerhard Bozinski, who is not with us today. He was not able to come. 89, when I was student in Moscow, I got a chance, absolutely, without, it was just invitation to spend one semester in Germany and to see research in Eifel Basin, which was exactly a prototype for Dmanisi. This was really organized, interdisciplinary, all volcanic area, etc. So this was some way chance. my touch with Western science, European science. And before also, I would like to thank my Russian professors, Professor Velichka, who is no more with us, and Professor Valery Alexeyev. They are helping me personally, not just to be formed, also to open eyes, to look big things. So excuse me, it's a little bit personal things I am telling you, but it's not just professional day for me and tomorrow. This is something part of life of many of us. So, and it's, you will excuse me a little bit my sentiments. So what happened in 91, and I will remember very well these days, this was exactly time period when politically was completely different. You saw this beautiful prospect you walked often on, Rustaveli. This was full with people and full with demonstrations, you know. And also it was, when we were in Dmanisi, this putsch happened in Moscow in 91, changing of the political system. So what I'm saying that it was completely different environment, and then it happens that the first team what we were, and I would like to say a few words of these people who already passed on. They are no more from first team. It's Professor Japari, it's a Professor Vekua, Merab Twalchrelidze passed away, Alex Muskhelishvili is no more, Nina Klapatovska. So half team almost is no more with us. But I'm happy to see Medea Nuradze strong, and she was the head of this Paleolithic group, the Jumberko Paliani, and young students, Gocha Kiladze, Teona, Georgi Nioradze, David Juane. So this was a story we started, Kivimai Suradze in 91. So Dmanisi had first 91 story with this famous premiere in Zенкенберг, which was really very high level of conference. And Friedman mentioned that we are 4 or 5. I think in this conference played a crucial role in Dmanisi's story. And you saw the one picture where Milford is looking, but also looking is Frank Clark Howell. Frank Clark Howell played was another person who played very important role in my personal career and in Dmanisi's story. We got friends, international friends, who were helping behind scene or just to have like, you know, a wind, blowing wind from the back. And this was Frank Clark Howell and the Leakey Foundation later. And I would stress with Leakey Foundation was very special support also, of course, through Ofer Bar Yosef, who was never really part of project either, Clark, but strongly helping us to build this infrastructure, what we call today Dmanisi project. So this was period of fighting where we will get Dmanisi, and you will see today continuity and story, scientific story of it. I think another important step started in 99 or 2000. And, you know, I could not imagine now, just when I saw here Anne Gibbons, that how Science magazine was somebody who helped us, you know. It's already old story. I could say now that it's very rare that this level scientific magazine is publishing already known news. And this was very rare exception of then Science magazine published these 2 skulls, which was already in media, it was presented and so on. And that's exactly you are getting help, exactly moment and how you are getting help. Team was developing, and I think it was very, when Reed Faring joined us in 93, or 93. Then we were enlarging, now Marta was 95, I think it happened. And Jordi, all this we were. So this was one stage. In 2000, we had also, then I would say, it was very special also support, including my French colleagues, Marie-Antoinette and Henri Delumley. This was connected with research, with some finds, but also helping to put also Dmanisi in public context. Beside of, it was first exhibition in Musée de l'Homme, which was, and also a conference in Tortavel. So this was support, scientific, going further than National Geographic, all these kind of things happened. And later, I think from 2002, we started to be more interdisciplinary. We got many new students. I would say today, I'm proud to say, at least there are 5 Georgians with international PhDs since that time, and different are also from other side. And this was time to bring real technological part, and Christoph and Marcia are not here. So this Zurich University connections which started, Philip Reitmeier became part of really strong team, etc. So today we are a little bit different, I would say, but it could not happen, may I say, without participation, every member of this team. You see, for example, pictures of 2 cooks, you know, Staliko and Luba, you know, anybody who was even one day in Dmanisi remember them. So I just want to start with thanks, you know, thanks, and thanks God that we got all of it. We are with you, and now we will present current stage of research. We will try to present our actual data. I will try not to go out of time limit, maybe contrary, to spare some time that we will have more chance to discussion. So we will have different speakers, but it does not mean it's not just their works, of course, this is whole teams. So, and first I would like to start with Reed Fehring. I couldn't imagine my professional life without him already. You know, it's another 25 years almost. And I wish that, we will not give anybody Reed, but you know, I wish that many young people will have mentor and colleague like Reed Fehring. And please Reed, you know, let's start it, right? And thanks once more, everybody, please.
Well, thank you very much, David, for that generous introduction. Next year will be my 25th year working in Georgia. I tried to get David and the people from Zенкенберg to wait for my 25, but they refused. So, so for me, it's 100 plus 24. And I have to share with David the incredible memories of the people we worked with here, and especially my gratitude to Ofer Bar Yosef, who called me in 1993 and said, "We have a grant to go to Georgia and we want you to come." So I came with Anna, Paul Goldberg, and Ofer, and we had an incredible visit. And then I had another phone call not long after that from Clark Howell, and he said, "Reed, we want you to do geology and dating at Dmanisi. It won't take you very long." He was wrong about that. I'm reminded of an introduction that Glenn Isaac made in one of his papers a long time ago about early work at Kubifora, and he said, basically, we haven't answered all the questions, but we know a lot more than when we started. And that's sort of where we are at Dmanisi today. So my challenge today is in a very short time to give you an overview of the site of Dmanisi and address questions of why it is such an important archaeological site and why it also has produced such incredibly unique fossils. So I always like to compare Dmanisi to the East African rift systems. Instead of, where is the, I don't have a pointer, it seems. Oh, is that it? Sorry. Oh. Instead of dispersed localities all over the rift valleys in East Africa, we're dealing with just a place, a small place on a landscape. But it is a unique opportunity then to see how people use this place over many, many occupations. It also raises the question of why should so many human fossils be preserved in this one location. Just by chance, the first excavations in Block 1 and Block 2, where the D211 mandible was found, and then later the two crania, happened to be just in the middle of the promontory, which turned out, to my pain, to be the most complicated part of the whole site. So for many years, we were struggling with the geology of that part of the site, and in that process, finding lots of fossils, but not giving me lots of profiles. So beginning in 2012, with support from the National Science Foundation, we began a program with two main emphases. One was to excavate a big block, a 25 square meter block, anyway, in M5, which you see over on the left side of that map, and then also a testing program to begin to get a better idea about the context of the fossils in the whole promontory. So we want to address a few questions. First, just to quickly answer the question, how old is Dmanisi? Most people seem to accept the ages that Carl Swisher and I proposed in 2000, which was right after the Olduvai Upper Matayama reversal 1.77 million years ago. Everything we have done since that time has supported that age estimate. But now we know much more about the occupation patterns at Dmanisi, and we also now can see that in the entire world of the early history of the genus Homo, Dmanisi has a completely unique set of formation processes, which we don't see in any other sites, which helps explain why we have so many fossils, so many well-preserved fossils of humans and animals, and why we have such a extensive record of occupations at the site. So the site can be dated by the lower boundary of the site is still the Mashavera basalt, which we dated, Carl Swisher dated at 1.85 million. And in that same process, it was actually incredible. In our first work in 95 and 96, I defined two major stratigraphic units, A and B. And a couple of months after we finished that work, Carl called and said, "You won't believe it, but all the A sediments have normal polarity and all the B sediments are reversed." So we, by great chance, one of the miracles of Dmanisi is that the Olduvai Matayama reversal is in the middle of our stratigraphic sequence. But upstream from Dmanisi, in two places now, we have a basalt that caps the Dmanisi sediments. And we published this in 2000, and then later at another locality closer to Dmanisi, working with the French team, we got the same ages, basically. So the Orismani basalt is dated at 1.76. So that means then that the entire record of Dmanisi has to fit between 1.78 and 1.76. So some of these wild claims that we could be as young as Jaramillo from some people are completely without any basis at all. However, within that time frame, I think that if we look at the soils and bone taphonomy, that the whole record of Dmanisi is a much shorter interval within this bracketed range. So, as I said, we found lots of artifacts, bones, and human fossils in blocks 1 and 2, but we wanted then to expand the excavations over the whole promontory. And so that testing program began with M5, and in 2005, for the first time, we found artifacts in the A strata. And so now, after those excavations, Teona, Sheely, and I did, we have almost 900 artifacts from that excavation block throughout most of the A strata and the overlying B strata as well. So this means that Dmanisi was being occupied repeatedly before the human fossils accumulated. This, of course, helps confirm the age of Dmanisi and the fact that the human fossils are in the middle of the whole sequence. Then we began the testing program away from M5 in Block 2, and M9, which is over 200 meters away from M5, I expected it to be completely eroded, being downslope, but to my surprise, we got another almost 7 meters of sediments and artifacts and bones, particularly in the upper layers, but we found evidence of occupations in both A sediments and B sediments as well. So this meant that the site was much larger than we would have guessed. And but in terms of putting the formation in context, we have a thick record at M5. 200 meters away, we have a thick record in M9. And in the middle, where all the human fossils are being recovered, we have a very different, compressed, and complicated stratigraphic picture. So just to show you a few examples of the other testing that we have done, M2, as you can see here, which is just southeast of the main excavation areas, has a very long sequence of occupations in both A sediments as well as B sediments. The triangles are lithic artifacts, the circles are cobbles, natural cobbles, and then the pound signs are bones. Down in M14, as you can see, we have a nice stratified series of occupations in both A sediments and B sediments. And then moving a few years ago, we began moving to the northwest, and here we haven't finished M18 yet. It's only 1 square, all of these tests are 1 square meter, by the way, so the fact that we have these kinds of recovery is pretty significant. We had to stop in M18 last summer because there's so many bones in the bottom. We have to expand the excavation so that we can do it properly. So you're beginning to get a picture that Dmanisi is a huge archaeological site with evidence of occupations in all of the A sediments and B sediments as well. And in particular, you can see here the correlation of these profiles, and in the middle would be the main excavation areas, which contain the very different geologic records. So one way to summarize Dmanisi is to divide it into 3 phases. The A phase represents the earliest occupations with stratified artifacts, bones, no human remains thus far. Above that, we have the late B phase, B2 through B5, again with stratified artifacts and faunas, but no human bones. And then in the middle, we have the B1 phase. And it is completely different from the rest. It is a phase of intensive geologic and geomorphic change, gullying, piping, which I'll describe. And it's important to note that all of the human bones that we have found thus far are from stratum B1. The other thing which I'll indicate is that the B1 phase should be measured not in thousands of years, but maybe hundreds of years. And the soils evidence and the bone taphonomy, as well as the pattern of piping at the site, are evidence to support that. Notice that, as Martha and Maya will say later, approximately 80% of all the bones that we have found at Dmanisi come from stratum B1. And this is a very short interval. So it's really an unprecedented accumulation of faunal remains and human remains. So now the results of the testing show, as of today, we have at least 40,000 square meters of in situ deposits at Dmanisi. And I suspect that that's going to be expanded if we move farther to the north and to the east. So it's a huge archaeological site. That translates to approximately 10 acres if you're from England or the United States. And now we have hominin fossils from 5 separate excavation areas, which also cover a tremendous part of the site. So the human fossils at Dmanisi are not just in one tiny place in Block 1 and Block 2, but are accumulating in multiple locations in the site, all in stratum B1. So the question is, why do we have so many human fossils, and why are they so well preserved? I joke with friends that this arrangement represents my classification of the Dmanisi fossils. We'll hear more about that later. One of the unique things about Dmanisi's formation history is the issue of pipes. Pipes are well-known geologic features. They're subterranean tunnel-like features that form not by dissolution. In fact, they're called pseudokarst. They're not karstic features, but rather subterranean erosional features. And in the central part of the site, Dmanisi is full of these pipes. Here's a pipe from eastern Georgia, a contemporary pipe, and you can see the opening of the pipe in this head wall of a gully. And then also important, just above that is a breach, which is a connection from the surface down into the pipe, which provides for objects, bones, and artifacts to enter the pipe that way. This also means that there are 2 ways that carnivores can enter pipes, and we have good evidence that carnivores were using these pipes as dens. Pipes are features that form and evolve into gullies in a very short time frame, a few decades at most. Here's a pipe in North Texas, near where I live, that formed in the cut wall of a quarry, and the entire life of this pipe, from formation to collapse and evolution to a gully, is 20 years. And that seems to match the other records of piping around the world. They're very short-term erosional features that evolve into gullies, which promote much broader patterns of erosion. So at Dmanisi, we had the perfect conditions for piping. All the pipes formed in stratum A sediments, and in particular stratum A1, which is a very poorly consolidated ash, very soft, and it's underlain by the Manchevero basalt and overlain by stratum A2, which is quite indurated. So we have the soft ashes packaged in between. Pipes have to have an opening. They have to have a place to release the sediments that they're eroding. And this was a big problem at first because we're in the middle of the promontory. Where are these sediments going? Then we found evidence of deep gullies, at least 2 of them now, as you can see here. And notice that they flank the areas of major excavations. After the gullies formed, there was an opening for the release of sediments, and so pipes initiated in stratum A1. And then pipes, as you can see, they are dispersed in all the directions away from the main excavation areas. Sediments began to accumulate within the pipes, and these contain lots of bones, and probably those were introduced by carnivores. Then we have good evidence for breaching these openings from the surface, which allowed for introduction of bones and artifacts from the surrounding surfaces. And So here I can show you two examples of breaches. The one on the right, this is the profile that Carl Swisher and I worked on in 1995 and 96, and it was actually this profile where I defined the boundary between the A and the B sediments. But there was a breach, and you can see that the D211 mandible was found in the breach fill, and its cranium was found in the pipe fill not far away. So this immediately showed us that the human bones were being introduced into the subsurface by the process of piping and breaching. Another example on the left is just north of the main excavations, and you can see the clear contact between the breach and the underlying pipe fill. So again, what we have then is, in all cases, all of the pipe deposits, all of the breach deposits yielded reverse polarity, and all of the A sediments were normal. So then the pipes and gullies began to fill up, and when the gullies filled, then the exit for the sediments was lost, which meant that the sediment being introduced by breaching and other means was blocked, and so we end up with filled pipes. So here is the best example. Those of you that are anxious to see this, I'll take you down into a medieval cellar where this is exposed. Carl and I sat in this medieval cellar for a couple of hours contemplating this profile, and it helped us understand completely that these pipes were after the A sediments and filled up later. So you can see the walls of the pipe here. Notice the meter scale. This pipe would have been big enough for people to walk in, basically. Certainly the Dmanisi people could have walked in. Another important thing is the lower pipe fill includes reworked A sediments and is very dark in color, but contains lots of bones. All of these pipe fill sediments, though, yielded reverse polarity. So some people have mistaken lower pipe fill for in situ A. This pipe farther up into block 2 collapsed, which is what pipes are supposed to do, is to collapse and turn into gullies. And this profile on the left is just a meter behind the profile that I showed you before, where the 211 mandible and the 2282 cranium were found. And it shows the bedded gully fill. I call those collapse gullies, as opposed to the primary gullies which enabled piping to begin in the first place. All of the human fossils that we have found then are found in pipe or gully sediments. This picture was taken just a few weeks before we found the 2700 cranium, and it was just below the big rack of deer antlers that you see there. To the left of those is a rhinoceros skull, and you can see the pipe wall. That pipe formed, then collapsed and turned into a gully, and the gully is filled with stratified bones, artifacts, and almost within the view of this photograph, we have about 60 human fossils. So the end of that story in block 2 was the thick gully deposits, B1XYZ. Those are just local facies names. They're not formal stratigraphic units. And in profile, then, you can see that almost all of the human fossils are found in B1X and B1Y as part of that gully that I showed you just a few minutes ago. So in those same gully deposits, I love the picture at the bottom because it has Canis etruscus and the big skull, big boy, the skull 5 in the background. And notice the density of bones in all of these, including an articulated elephant foot that you can see on exhibit out here. The density of bones here is just phenomenal. It took us 7 or 8 years to excavate 1 square meter in this part of the site that is so full of bones. So this immediately raised the question, why so many bones? Why are they so well preserved? And why does it appear based on soils evidence and bone taphonomy, that this all happened so quickly. Well, the rest of the story is that all of the pipe and gully features were filled up with new airfall deposits. Normally, a piping system would evolve into gullies and part of a long record of slope erosion, but the addition of new aeolian deposits, both ashes, and now we can say, beginning with B sediments, we're also seeing a significant component of loess. All of these new airfall deposits filled up all of the pipe and gully features, and after that, the Dmanisi site was a level surface again, following normal surface processes of geology. So there are no pipes before stratum B1 and no pipes after stratum B1. So it's a very short phase of piping activity. And so the red dots up there show you the context. All of the human fossils that we have so far are in pipe or gully deposits, and those are all concentrated in the central part of the site. Notice that the basalt drops significantly to the east as we go off, and that probably contributed to the formation of gullies. So all the hominin fossils that we have found fit into these ovals, both stratigraphically and spatially, and they're all associated with pipes, gullies, or dens. Going back to M5, we didn't get a lot of fauna at M5, but the pattern is significant and matches what we're seeing in the rest of the site. And in red, you can see the carnivores, which are present in features in stratum B1. So this map of this is the M5 block. The strange shape is because we were surrounded by medieval walls, but we found 4 carnivore dens in M1. I asked Rick Potts to confirm my recollection of the literature that in Africa there are no sites that have physical dens in the site itself. Maybe. Anyway, okay, but not very common. Dmanisi appears to be full of carnivore dens. And these are all emanating from the B1 surface, which means that the carnivore denning and human occupations are basically coeval. So humans and carnivores are using the promontory, maybe not exactly at the same time, but certainly repeatedly over the interval of B1 deposition. And so we have carnivore dens that were excavated, like the one at the top, but also the pipes served as carnivore dens. This may be one of the reasons why carnivores were attracted to the site, but regardless, we can show that carnivores and humans were using the site repeatedly throughout stratum B1 deposition. That means that humans and carnivores like this had a great chance of meeting one another at the site. And we don't know exactly how all the humans died at Dmanisi, but you know, to make it a good story, I would say that a lot of them may have encountered carnivores in the process of scavenging at the site. At the very least, they were visiting the site pretty much at the same time. Related to that is this interesting feature in block M5. I showed this picture at a talk a long time ago, and I was sorry that Rick Potts wasn't there because we found this incredible concentration of these cobbles in the corner of our M5 excavation. These have to be manuports, have to be placed there for some reason, and I would suggest that the evidence is circumstantial in all cases, but they were not there for making flakes, I can tell you that. We have the same situation in all of the pipe and gully features. We find a lot of natural, unmodified cobbles there. So the whole idea of throwing stones was one that I was indoctrinated into by Barbara Isaac in our early years. And so I think it's a long story, of course, and it will always be a circumstantial story, one of context and association. But all of the unmodified cobbles are being concentrated near the pipes and gullies, which suggests to me maybe aggressive scavenging as opposed to defensive scavenging. So it's very possible that the humans were taking carcasses away from other carnivores at the site, but we'll see. So in the end, then, we have this phenomenal phase, the B1 phase, with pipes and gullies and dens, with humans interacting with carnivores, carnivores eating all kinds of big game, humans, as Martha will show you, humans eating lots of big games, and as usual, the relationships between carnivores and humans is interesting. So, the Dmanisi hominins, as we've all heard about before, no one expected these people to be here. They're so small, their brains are small. But now the anatomical work done by all the fine physical anthropologists have shown that Herman Ponzer's work on the feet and legs was really fascinating, that they were fully capable of endurance running and efficient walking, etc. And we have a lot of hand fossils as well, the numerous basalt artifacts, which are very difficult to make, to me, prove that these people had very strong grip strength. And the shoulder, we have the shoulder anatomy as well from Dmanisi, which shows that they were certainly capable of throwing. So Dmanisi has an incredible story of artifacts and human anatomy and associations with faunas that give us such a unique record at this stage of human evolution. So Dmanisi is not just a place that produced lots of beautiful human fossils, but it also is a place that has produced an incredible record of human activities and changing behavioral use at the promontory. No evidence for culture change. We don't have developed Oldowan A or B. We just have one basic technological scheme, but we do have excellent evidence for different activities and different patterns of use. Basically, we have all of Glenn Isaac's site types at Dmanisi, where napping of stones was predominant, butchering of animals was predominant, or just a natural accumulation of animal bones without artifacts as well. So 40,000 square meters represents lots of work for David's new generation of Georgian archaeologists, and hopefully many other scientists from around the world as well. So thank you very much.
How do you prefer to ask immediately questions or listen after? Prego, yes. Please.
Yes, so do I understand correctly that all of the infilling sediments within the pipes, you said, are reverse?
Yes.
So they're all of the pipes, including the fauna and the homs, must be above the old one.
Exactly.
And so that's why you have that.
Right. But if we look at soil development and we look at bone taphonomy, as we, Carl and I had a big argument. He wanted to say Dmanisi was 1.6, and I said no, it has to be much closer to the reversal. I don't see 200,000 years. So it has to be very soon after the Olduvai-Matiana reversal. Yes?
What makes you think that the cobbles was for growing opposed to ultimately being used for flaking?
Well, because the cobbles include raw materials which are of very poor quality that they never made artifacts from. So, and they were also, I think they were scavenging there are 44 pieces in 1 square meter. Some of those are actually cores, which I think they just scavenged and placed there as well. So if we look at the use of different raw materials, the cobble inventory is different from the profile of materials that were used for making artifacts.
So, thank you, very, very helpful. Could you say a little bit more about the broader landscape context of where, what was the topography and the position
Yes, very important points. Dmanisi is at the confluence of two rivers, the Mashavera flowing from the west, Pinos Varis from the south. It's also at an ecotone between the more mountainous forested parts of eastern Georgia, western Georgia, versus the more open steppic environments of East Georgia. So we're in not only an ecotone, but we're on a major pathway for animal movements along the river valleys.
That confluence is as old as the site.
Yeah. What's fascinating, I can show you on Saturday when we go there, is that the Mashavera basalt came from the west and filled up that valley. So the bottom of the Mashavera basalt shows us exactly the topography before the occupations. So the rivers were in exactly the same location as they are today. I think the hills were in the same configuration topographically at the time. And so the modern landscape at Dmanisi is really pretty, other than human modifications, is pretty representative of what existed then. But this mosaic of environments that our colleagues will talk about later, of forest-dwelling things, deer are very common in the assemblages, as are other open dwelling animals, rhino, horses, elephants, etc. So we have a nice mixture of open environments as well as patches of forest. Yes.
Yes. You mentioned that there were several carnivore dens, and so the carnivores must have been able to get in and out regularly of the cavities. But and you also mentioned that the carnivores were dragging many of the bones to the area. But is there any evidence that the shape of the cavities at some point could help them act as traps? I mean, not only having dens where the animals could enter freely and get out, but if there could at some points be deeper or more steep walled cavities which could act as traps.
Right. We've thought about that a lot. One issue in that regard is the fact that none of these are very big these are not big features. So I don't think they were driving animals into the gullies to kill them. But certainly the persistent association of dense bone accumulations and artifacts in the gully and pipe features suggests that there was lots of opportunities for them to encounter animals in the pipes, etc. The Martha's data shows that none of these bones were transported any great distance. So this means that even like in Block 2, where we have thousands of bones, they must have accumulated very near the gully features that we excavated. So somebody, when I think of stratum B1, I just say somebody rang the dinner bell. There was a lot of animal activity going on and lots of animals being eaten by carnivores, and we presume people as well.
I think Marta will answer this.
Yeah. Okay.
Now I will ask Marta Tappen, and it's a group, and also when I mentioned about some Georgians PhD, also it's my pleasure to congratulate the Reed Cole. He just got PhD, also Marta's students, on the Dmanisi material. So that's a good news. Please, Marta. And another veteran, right?
Yeah. Okay, well, it's great to be here. I'm so pleased that this conference is being held in Georgia, and And I think the organizers have done a really nice job, and I don't know, it just makes me very happy. I've been studying the large mammal vertebrate taphonomy of the site, and it's really exciting, and there are so many aspects to it to talk about. So I thought that I would just give an overview of the basic parameters that we see at the site. And just to explain, it's the reason why the taphonomy is so interesting is because it can give us clues as to how well the site is, the fauna is representing the mammals, how accurately they're representing the mammals in the biocenosis. So you have the biocenosis, the living community, and then what we have, of course, is the taphocenosis, the taphonomic, the buried assemblage. And we want to know how accurately it reflects the living assemblage. And of course, we want to know how the site formed and if there are any clues as to Homo erectus's behavior. Is okay? No, it works. Okay, I just okay. So this is my sample, and I do not have all the bones from the site. So I have about, I don't know, over 80% of the bones in my taphonomic sample, and of course excavations keep going. And this is by the NISP, or number of specimens by test block, and let's see, is that the pointer? Is that point? Do you know which is the point? At the top you can see. Did it point? Okay, well, at the top you have Block 2 North, and Block 2 North has our largest assemblage, and you can see we have nearly 3,500 specimens. This only includes mapped specimens and things that were identifiable in the screen. So I went through all the wet screening, or as much of the wet screening and the dry screening as I could, and if they're identifiable, I put them in here. So, so Block 2 North is from the 59 grid line and is from 2001 excavations when I began to be on the site all the time. And the Block 2 South is also a large area with lots of bones, but the reason we have to separate those is because we use two different nomenclatures for the stratigraphy. I've been obsessed this past year with getting the bones in the right microstratigraphic context, because if we don't have that context, we won't be sure what we're talking about. So this is what I've done the past year, working with referring and profiles and making sure things are in the right context. M6 has 1,100 bones, 7 square meters excavated. Building 11 from earlier in the 90s has a huge sample. And then you can see the samples that we have from the different excavations. M5, of course, is really important. It doesn't have a huge assemblage, but it has the stratigraphic control without the gullying and pipes. And M17 and M11 are being excavated now, and they're not in this. So what we see is that 88% of the bones come from the B1 strata, and this is, again, where I have the most control, Block 2 North, M6, and M5. And you can see the counts there. It's important, though, in the A sediments, this is what I have for the A sediments, very small samples, so I can't do statistics on those or anything much. I'm going to concentrate on B1, but it's important to note that B2, B3, and I think B4 all have Oldowan archaeological sites, so they're very important also. Okay, this is the number, accounts by family. Can I stand here and talk? Loud enough? You want me up here? Okay. These are the counts by family using a number of specimens by the different layers. So we have, the brown is B1, B2, and B3. The actual, the species represented will be presented by Maya Bukshanidze this afternoon. So I'm only presenting here proportions of families of large mammals. And it's interesting to look at. So if you look at B1 first, the most anterior one, Cervidae are by far the largest group that we have at the site. The first bar is how many are not identified, which is also large, but even larger than B2 and B3. There's a lot of bovids and equids, and you can see the large animals like giraffes, elephants, rhinos are in smaller numbers, and but up pops the equids. There's a lot of equids and a lot of canids. And if you look at B2 and B3, so this could represent change through time, remembering that the sample size gets much smaller, you have really the same situation, except for that there's a lot of non-identifiable bone in B2 and B3. And B2 and B3, of course, sat out longer. They weren't buried as quickly. There's paleosol formation in those, as Professor Fehring said. So, and they all are dominated by cervids. There are possibly more equids in B3 and more bovids, which could be interesting, but I think we need to dig more to find that for sure. Okay, so I thought it would be interesting to look at the proportion of families compared to an East African ecosystem. And not because I was really thinking that it's going to be just like East Africa, but because we always use East Africa as our models for what early Homo habitats are like. And so I used a number of individuals from a paper in Science this year by Hatton et al. And I compared Dmanisi to Amboseli, Serengeti, and Ngorongoro, the living faunas. And I'm using NISP here. You realize that if NISP, number of identified specimens, has been shown to correlate highly with MNI and is considered to be a less derived counting mechanism, and is a very good way to count bones, except for in some situations. Anyway, so this is number of specimens, and what I did was I lumped cervids and bovids because there are no cervids in Africa, and so this sort of ruminant category, and you can see if you look at that, the top, the Dmanisi has a fewer ruminants than the African sites. if you look at the equidae, Dmanisi is right within the range of the African modern savanna. If you look at Canidae, Dmanisi has a whole lot. And again, why are there so many canids at Dmanisi? An interesting question. But remember also, and I'll come to it later, but also there should be more. There are basically virtually extinct in East Africa now from overhunting. So that's East Africa's fault, not that they're missing, not mine. And then the felids, we have a lot of felids again. We're in red there, lots of felids. And hyenas kind of in the same range as seen in these African sites. And of course, we have bears, and they don't. And we have pigs. I mean, they have pigs, and we don't. And so those are some of the differences. And we have higher rhinos. And again, I think that may be due to overhunting. And they barely show up in the African assemblages. And then the elephants, similar situation. And we don't have hippos. Anyway, so you see a structure here that's overall quite similar, except that we have a few more carnivores than expected, and we're missing some of the habitat, there's some differences between the African faunas and Eurasian faunas. Of course, pigs, bears. And we have no aquatic animals. Okay, but I want to, yeah. Oh, good, because I wanted to point. Okay, and what I did now was I separated the fauna by substratum in block 2 because we had the most control. You can see our sample sizes here of 900 or more than 900 in B1Y and B1X, B1Z 524, and the numbers getting smaller. But I just wanted to show you that B1Z are the gullies, and B1Y is more at the base near the, like where Skull 5 was found. Okay, have fun, yeah, good, there, okay. Okay, the Dmanisi assemblage is not weathered to any extent, especially if you're looking in B1. And if you look in B1, I suppose I should be looking here. If you look in B1, if you add weathering stage 0 and 1 together, 96% of the bones are in 0 or 1. That means that they weren't exposed on the surface directly into sunlight. Now, bones can stop weathering in the shade, and they can stop weathering if they're in a pipe and not exposed to the sun. And you see here, as expected, the weathering is higher in B3 and B2. There's more in higher weathering stages, especially B3. And B1A, which is the in situ ash fall. In block 2, you can see there's a little bit more weathering there. But these are very similar to each other. And it indicates the bones were deposited very rapidly and buried very rapidly. Whole bones. So about a quarter of the bones are whole from the site. But if you look especially in B1X, you see there are 37% of the bones are whole, okay? And B1X and B1Z, we have some nearly whole individuals, but that's not really true in B1Y. So here you can see also that when they are broken, the bones were broken while they were fresh. So we don't have post-fossilization breaks unless they were made by anthropologists. And that happens, you know, that happens. But if you're digging out a bone, it comes out with only curved, high-angled breaks with the same color on the edge of the breaks. Okay. So depending on what layer you are, most of the bones are found as isolated specimens or as segments of articulated units, but not usually as whole individuals. And B1Z has a few whole or nearly whole axial skeletons. So down here at the lowest picture, you can see this is B1Y, and you can see that there are bones from several different species, you know, including humans, right there. And this is same as, but bovid, scapula, ursus, ulna, and they're all there, but they're not really articulated or anything. If you go up to B1X, you still don't see very many articulated specimens, but you know, in any of these layers, this can happen. An articulated limb or a segment of a vertebral column, but not usually a whole animal. And then if you get up in B1Z, we had several animals that looked like they must have just died right there because they had articulated torsos. But in any case, the fauna is not sorted by size or skeletal element. So in addition to these big bones that you can see, we have 1,000 long bone shaft fragments and other fragments of bones. And you can do all the analyses of size sorting, and my student Reed Coyle did that. What we find is it's not size sorted by element or by size. So these things are looking like it's not transported. Okay, bone surfaces. Despite the great preservation at the site, bone surface analysis is not as easy as I would like it to be. What happens is that there's a lot of fungal etching on bones here, and that can block any kind of looking for surface marks. And there's a lot of calcrete and matrix adhering to the bones, which can make it very difficult when you're looking at like the gnaw mark that's there, but difficult to measure and everything, and difficult to count how many there are when you have that kind of calcrete and matrix. The evidence for abrasion, like if they were scratching against the sediments, is very low, okay? And we have the percentages here, and you can see the percentage of bones with, this is an abraded bone, it has scratches going both ways, but it's a very rare kind of thing, usually on, you know, 1% or 2% of the bones. And we don't think rodents played a big role either, because we don't have enough rodent gnawing. A Hystrix den is expected to have 60 to 100% of its bones with Hystrix gnawing on it. And we don't have anything like that. What we do have is a lot of carnivore gnawing on the bones. And here I've separated it again by stratigraphic level. I have some pictures of some of the carnivore gnawing. And if you look at the percentage of tooth marks at the site, you see that B1X and B1Y have about 20% tooth marks. But if you also add these very characteristic breaks without tooth marks, crenulated edges, etc., you get closer to 23% or 24% of the fauna has carnivore gnaw marks on it. This means that the carnivores were active at the site and were consuming the animals. You can look at the tooth pit sizes, and I've plotted the Dmanisi tooth pit sizes here on a graph with actualistic data from different species that, this graph was made by Delaney et al. The circles go around what the lions and hyenas do. That's our mean in a confidence interval. What you see then is this is only for cancellous bone, because tooth marks only tell you the size of the animal if you have cancellous bone, because it's very hard for the animals to mark cortical bone, and so the actualistic studies show there's too much overlap in body size in the tooth marks. And what you see is that we have large carnivore tooth marks like the super predators, like the modern lion, and like the modern hyena, and going up bigger or just as big as it can go. But we also have small tooth marks. So, and these are starting to be too small to be the size of our large carnivores. So probably some canis tooth marks also. We have hyena and cat marks, the large cats probably. We have more evidence that carnivores were living at the site in the form of coprolites. We have 161 coprolites in total. As you can see here, the counts are by excavation block and by stratum. And what you can see is that the most coprolites are in B1. If you look at B1, Block 2 North, 102 coprolites. These coprolites are mostly hyena, but some of them are elongated and represent other carnivore species. And and some of them are small. They look like baby hyenas, maybe. So B1 has tons of coprolites. This fits with our ideas with the carnivore gnawing. It fits with the ideas of using the pipes as dens, maybe digging some of the pipes out even bigger, and certainly eating the animals at the site. The other parts of the site from the older excavations may have had more coprolites, but they might not have been all kept. Some of them were. Okay. Now remember, we talked about how there were too many Canidae at Dmanisi. And the Canidae and the hyena, Pachycracuda, they have different taphonomic signals from each other. And I think this is why they show up so much on a graph using NISP. What you can do is you can do a ratio of the number of bones per individual. And I did it here by layer, and let's see. For hyenas, we have only 2 bones per individual. That means they're just fragmented, and or you know, you find a tooth or one broken limb bone, or you know, a small bit of hyena here and there. And if you start counting up the MNIs, it's just not very many individuals. Canis etruscus, we have more individuals, but they also have more bones per individual. And so it looks like Canis often is not crunched up. The Canis bones were introduced often whole, and they we haven't found like a whole dog, but we've found parts of Canis etruscus, including parts of vertebral columns, and those numbers of bones add up quickly. So I think the Canis shows up quite high because they are more whole than Pachycracuda. Let's see. Here's some Canis skulls. This is from Dmanisi. This one is from a hyena den in Israel. And this happens at hyena dens. So my point is that hyenas kill canids just probably out of competition, but they often don't eat them completely. They just drag them in there and, I don't know, trophy hunting. Okay. Now the big cats. So the big cats are also, you know, they're prevalent. We have more species of big cats. We have MNIs of at least 5 Homotherium, at least 5 Megantherium, at least 3 Panthera, I don't know, 1 Asionyx that I know of, and a couple lynx. And so the cats are very predominant. We have juvenile cats. And here is a Homotherium skull that has this irregular crunching and a carnivore tooth mark on it. And I think that a Homotherium was crunched by Pachycracuda, probably. I say that because Pachycracuda crunches bones the most, and because it's a big crunching, big tooth mark. Happened right at the site. It didn't get transported. It couldn't have. Okay, and then hominins. But it's not just carnivore. Hominins are at the site, and they're eating meat. And what you see is there's only about 30 cut marks from Dmanisi, which is a very low number, but a lot of the early sites have very low numbers. We can still say something about these marks. We can say that we have cut marks on the upper limb bones. These are the meaty areas, and generally that means early access to a carcass, because that's where the carnivores would eat first. So it means early access, probably hunting and or scavenging. We have cut marks. On the next page, you'll see this on Mammuthus. And if you're doing mammoths, maybe you're scavenging. We have cut marks near joints that would indicate disarticulation. We have cut marks on distal limbs that probably indicate skinning. And we have some hammerstone breakage. But I find that people are not being careful enough with their hammerstone breakage and generally in taphonomy. And we're trying to be very careful, but we do have hammerstone breakage. Okay, and you know, some other really interesting clues is that there are cut marks on several large taxa of mammals. We have cut marks on the rib of a mammoth. We have cut marks on Stephanorhinus, the rhino, Equus, Deinonychus. We have cut marks on the small deer, Pseudodominesti, time's up, and yeah, these guys here. Canis etruscus is our only one with, only carnivore with cut marks. That might be interesting. Maybe they're only being able to capture the Canis compared to the larger ones. Okay, and I'm just going to say a couple words about the taphonomy of the humans, and that is that most of them are not modified by carnivores. They're not weathered like the rest of the bones. They have a mortality profile that can be considered attritional because there's two subadults, or a subadult, two elderly, but that's too small of a sample to say that, really, but I like to anyway. And they're in layers B1Y, Z, and X. and they're whole or mostly whole. So I think I'll conclude with that, saying that there's actually we do have some gnaw marks. There's a long bone over there on the far side with tooth marks on it. So the humans and the carnivores were eating each other at the site. So I'll just conclude with that the last phase of the site is some slumpage into the site, into the low parts of the low part of the basalt, but it's not real transport. So thank you.
Any questions now or coffee break? I think I would suggest to have a coffee break, as it will, and to move Philip's talk after coffee break. You don't mind, I imagine, right? Very good. So we are now 10:30, right? Can we have coffee break 20 minutes? So, and 10:50 we will continue with Philip will be first, and then we will be fully hominid before lunch. Who will eat hominids? Very good. he told me, asked me I don't know how many times. And I said, not yet. And, Tuesday morning, and it was also an interesting story. It was in one of squares. Lazy Georgian boys were excavating there. I think one was Georgi, Gocha, I cannot remember one another. Were too many bones, and they were tired with these two drawings. And then this German girl, Auntie Eustace, said, no, I will work there. And this was the day when mandible arrived, right? So this mandible pushed us towards putting Georgia and Dmanisi in paleoanthropological map, and we are often remembered now saying this Frankfurt conference, and one of the main participants, very elegant, serious professor, Philip Reitmeier, since 2001 is member of our team, and I'm very proud to invite you. So 15 years, your birthday, 15 years your presence in Georgia, so another date. You see, so slowly we are finding more and more things, you know, to celebrate. Please, Philip.
Well, thank you, David, and good morning, everyone. Good morning again. I have just a couple of quick words to say at the start. I have indeed worked in Georgia for 15 years, and I've enjoyed every moment of it. I feel privileged to have spent time in the museum and at the site with my many colleagues and friends. I've learned a lot. I hope that process isn't quite complete. I'm very grateful for the opportunity to contribute to the Dmanisi research effort. Since 1991, the site has produced a number of hominin fossils. You've already seen illustrations of most of them, and you've been through the exhibits, so there's nothing new here. One of the more intriguing discoveries made in 2000 was the D2600 mandible, shown up here. Right away, the jaw appeared to be distinctive. It's much larger than the first mandible, D211, and indeed, D2600 pushes the limits of size variation as we know them for Homo erectus. D2600 also bears abundant signs of pathology. I won't discuss any of that. The teeth are very worn and there are consequences. Annie Margvelashvili will talk more about the pathology of the specimens later on this afternoon. Fortunately, several years after the discovery of the D2600 mandible, the rest of the head appeared at Dmanisi. It was a very fortunate discovery, but not entirely unexpected. Indeed, I had had a bet with one of the paleontologists here, Basilam Vecua, about whether or not such an item would be recovered, and if it were, just what it would look like. We sealed the bet with Chacha in his office, but I'm still not sure who won, so time will tell. Brain volume for skull 5 is a mere 546 cc's. It's very small, that is, skull 5 is, in terms of its cranial capacity at any rate, the smallest of the Dmanisi hominins. This is a bit surprising, since at the same time, skull 5 looks very much a male. This runs contrary to expectations, as of course, for most primates, males tend to be the larger members of the species and females are a bit smaller. There are always exceptions to these rules, especially in biology. Skull 5 is distinctive in its very low cranial height, very long projecting maxillary clivus. Indeed, the face is rather muzzle-like, and in that respect it resembles the face of earlier Australopithecus afarensis in particular. The teeth are large, especially the molar teeth are large, and for skull 5, the M3s are among the largest in the hominin record, approaching those of Zinjanthropus or Paranthropus boisei in size. Now, the discovery of D2600 followed by the discovery of D4500, of course, raises the possibility of taxic diversity at the site. This has been an issue for some time, the question of whether or not the Dmanisi hominins, all 5 of the skulls, belong to one population accumulated over a short period in time, as you've heard, in one place, or whether it's possible that several taxa may have crept into this assemblage. This is an issue, I think, that has still to be fully resolved. For the last 8 or 10 years, members of our team and other folks as well have carried out a series of resampling analyses in order to address just this very question, to test the null hypothesis, the obvious null hypothesis in this case, being that the 5 individuals at Dmanisi document one group, one taxon. Previous attempts in this regard suggest that the Dmanisi mandibles, taken as pairs, for some dimensions anyway, exceed the expectations for pan-troglodytes and certainly modern humans. Shape variation, on the other hand, shape variation among the crania seems to be comparable to that within pandemes and in recent humans. We've done some further checking, not with resampling approaches, but with CV or V, coefficient of variation. It's clear that endocranial volume at Dmanisi is not a problem. That is, the variation at Dmanisi is quite comparable to that in recent humans, also in Homo erectus, in several other comparator groups. This was the subject of one of the posters, which is maybe still up outside. Cranial height is quite variable at Dmanisi. Cranial height and parietal length are probably more variable at our site than in comparator groups, including Paranthropus and earlier Homo. But for other measurements, variation at Dmanisi is consistently less than or equal to that for the comparator populations. At Dmanisi, even some of the facial measurements, cheek and nasal dimensions, are less variable than in the comparator taxa. We infer from this, it's quite likely that the Dmanisi specimens are drawn from a single population. If that is the case, then an obvious next question is whether the Dmanisi assemblage as a group can be placed within Homo erectus as we generally understand it. That is a rather all-inclusive taxon with specimens from Africa as well as Asia. Or alternatively, it's possible that the Dmanisi specimens should be grouped with earlier Homo, perhaps with Homo habilis, perhaps with Homo rudolfensis. There are examples here of these taxa. Skull 5 is compared to the best specimens of African Homo erectus up above. Obviously, there are some similarities in cranial contour, some differences in size. Not so much skull 5, but certainly a couple of the other Dmanisi individuals do resemble Homo habilis. Particularly, there are similarities between D2700, the subadult cranium, and KNMER 1813 from Kubifura. Some of that is affected by development, the fact that D2700 is indeed a juvenile. On balance, it seems to us that skull 5 is not particularly like Homo rudolfensis. Now, This sort of comparison is facilitated by various approaches. One heavily used and useful approach is principal components analysis, which you see here, based on 10 size-adjusted cranial variables. Just the cranial vault is included, unfortunately for Homo erectus, which is the principal target for comparison. Very few faces are preserved. What you see here are two clouds of points, two distributions, one in darker gray, giving the 95% density contours for a variety of Homo erectus, as I said, both from Africa and Asia. There is, if you can pick it out, a slightly less gray cloud off to the side, off to the left-hand side. That is the density distribution for the Homo erectus crania. You'll see that just one of the Dmanisi specimens actually is included within the Homo erectus contour. The others are outside. Also, several of the Dmanisi specimens, D3444, that's the old toothless guy, and D2700, the subadult, fall close in principal component space here to Homo habilis. I should point out that the first axis here is driven not by brain size, but rather by mandibular fossa breadth, which turns out to be important. Larger mandibular fossae, wider ones are off to the minus side. Least frontal breadth or cranial narrowing, frontal narrowing is also important on axis 1, and of course skull height. Principal component 2 is driven by supraorbital torus form. Remember, these are all size-adjusted cranial dimensions. So the highlights, the principal points to be drawn here. I've mentioned several of them. Firstly, only one of the Dmanisi skulls seems to fit comfortably within the confines of Homo erectus. Others generally do not. Those that do not seem to lie close in hyperspace to individuals referred to Homo habilis. I would say principal components analysis seems to provide little support for the hypothesis grouping Dmanisi within the Homo erectus hypodyne. The best explanation here, for me, inferred not just from principal components analysis, but from many other detailed approaches to the specimens, is that there is in fact a continuum of form at Dmanisi. Skull 5 here is the most primitive in terms of brain size, of course, and overall proportions. Skulls 2 and 3 are more gracile with rounded occipitals. Skull 4 has a more globular vault, and skull 1, the first cranium to be recovered from block 1, is in fact the most similar in form to Homo erectus. That's the one that in hyperspace lies within the Homo erectus distribution. Given this result, how are we to accommodate the Dmanisi population within available taxonomic frameworks? Now, here is one available taxonomic framework. It's impressive indeed. This is, by admission of the authors, a particularly speciose version of hominin taxonomy, produced by Bernard Wood and Eve Boyle and published very recently in the Yearbook of Physical Anthropology. Some of us refer to these as woodograms. There are many taxa here, all in glowing color. I've outlined in the box in the upper left-hand corner the Homo taxa, various species of Homo. There are a number of them. One possibility, given the outcome from principal components and other comparisons, is that the Dmanisi fossils should be allocated, of course, not to Homo erectus or to Homo habilis, but to a third species, Homo georgicus. Such a decision would recognize at least 9 species of Homo, not counting Homo helmii, Homo naledi, or Homo floresiensis. And there would be at least 5 species of earlier Homo, 4 of which lived not exactly at the same time perhaps, but lived within the confines of the Turkana Basin in East Africa. Now, before we get carried away here, let me point out it's important to remember that species are biological entities. They are sets of populations sharing characteristics. They may be paleontological lineages maintaining their identities through time. This implies different patterns of resource exploitation. This implies different patterns of niche differentiation. The question arises then as to what adaptive differences might allow up to 4 species of Homo to inhabit one area in East Africa, one lake basin, at about the same time. Now, I want to address this question just very briefly. An obvious question is whether diet is involved here, dietary differences that might allow the different species to adapt separately to their surroundings in the basin. These are just carbon isotopic ratios, preference for C4 toward the top, preference for C3 vegetation toward the bottom of the chart. These are Homo specimens, all of them from the Turkana Basin. Some are earlier Homo. Many of them are distributed toward the bottom of the chart. Others are clearly Homo erectus up toward the top. There are 2 teeth there that are in fact drawn from one individual, KNMER 3733, Homo erectus from Kubifura. There is a trend, clearly there is a trend toward increasing reliance on C4 resources in the case of Homo erectus as opposed to Homo habilis or Homo rudolfensis. But at the same time, I would say that carbon isotopic ratios do not inform us a great deal. Certainly they don't tell us much about meat consumption, which is one of the principal questions. Additional information as to the type of diet consumed must come from other approaches, must come perhaps from studies of dental microwear. Here again, I don't want to talk at great length. Samples, of course, for dental microwear studies for these earlier African hominins are still quite sparse. Many of the teeth aren't appropriately preserved. Probably earlier Homo did not typically eat extremely fracture-resistant foods. Dried meat are USOs. USOs are underground storage organs, tubers, corms, roots, things of that sort. However, Homo erectus may have consumed more tough material. This is a quick summary of a lot of stuff that's been published over the last decade. Homo erectus may, in fact, have consumed more tough material, perhaps more animal tissue, some USOs, in comparison to Homo habilis. Nevertheless, at present, there is not a lot of evidence for dietary differences within these groups. So let me show you one more diagram here. I would say, given the story so far, that perhaps there has been too much emphasis on clade formation, too much emphasis on cladogenesis as the basis for macroevolutionary change within our genus. Just have a quick look at part C of this figure, the lower left-hand figure. That provides a depiction of Homo erectus evolving from Homo habilis as a separate lineage. And one alternative is to place the Dmanisi sample right at the base of the Homo erectus line. An alternative, which I prefer at this point, is depicted in part B of the diagram. This suggests that there was a single evolutionary species, Homo habilis plus Homo erectus, evolving in East Africa and eventually in Asia also. And here Dmanisi is placed in an intermediate position between Homo habilis on the early end and Homo erectus a bit later on. In conclusion, some of this you can surely read for yourselves. Proliferation of lineages in the period 2.5 to 1.0 million years ago is indeed well documented. We've just showed you the widogram of the moment. But the evidence for bushiness, I think, perhaps I should say the evidence for woodiness within Homo, I think remains equivocal. The picture has in fact become less clear as new fossils are discovered. If Dmanisi has taught us anything, as far as the hominins are concerned, it has revealed to us the fact that we should expect to see much variation in the record. Variation is a fact of biology. We should expect to see variation not just at Dmanisi, not just in Western Asia, but in the African record as well. Given the resemblances of Dmanisi to both Homo habilis and to Homo erectus, to me at least it seems reasonable to place all of these fossils within a single evolutionary lineage. It then becomes a matter of taste whether one continues to use the terms Homo habilis and Homo erectus, which is the option I would prefer, or whether one simply subsumes all those populations into one taxon and one name. Under this last hypothesis, it's not necessary to explain the potential sympatry of multiple Homo lineages in the Turkana Basin or elsewhere. Populations of just one evolutionary species inhabited similar ecological niches based on foraging and the acquisition of animal protein. So thank you for listening. Thank you very much.
Thank you, Philip. Maybe some questions immediately or after. What do you prefer? There are questions? Or later? Okay. Okay, now we will move to next speakers. When in this 91 conference, I had the chance first time to see in paleoanthropology using computer-assisted paleoanthropology was presentation, Fred's Full and so on. At that time, to compare with what is today, I think very big difference. And since 98, I have the pleasure to meet the first time Christophe and Marcia, and then later, I think their involvement in Dmanisi was crucial for the development this direction, but not that this direction. What we learned and what we try and what we are sharing there. This is a tool. It's not just simple, may I say, using scanners or any so-called now new equipment. How you can understand it and how to bring, and hopefully you agree with me that Christophe is one of the pioneers really to bring, in this case, art, some way, art approach. And for me, it's something which is part of really this long-term vision, what we try to continue and to have, that not to be like Dmanisi have, simple way we are splitters or lumpers, to bring something which is much more and much more complex things. And I really am happy that I have a chance now to ask Christophe and then Marcia to talk with you and to present work which is almost 15 years, right? So, also you were in 2001 first time, right, in Georgia? Yeah, so one jubilee we could share together.
Thank you, Dato, for this nice introduction. Have you ever heard about the Niels Bohr paradox? It just crossed my mind. So, you know, quantum physics, if you try to force a photon to go through one hole, but you have two holes, it will actually go through both ways, but you can only observe one. So what's happening to the other possibility? And Niels Bohr said, well, every quantum decision opens up a new universe. And then other people say, that's a beautiful explanation, but we are running out of universes at some point. And what Philip told at the end basically reminded me of that. We can actually create many more human species, and this makes things easy, but we are running out of ecological niches. That's the problem. Okay, so let's start with some, I would say, some thoughts on what Dmanisi can tell us in terms of what's the meaning of variation. I'm going to talk about the phylogenetic implications of variation, and later on you will hear about ontogenetic and in vivo patterns of variation. Everything boils down to the question that we had to ask ourselves many years ago. You have these 5 individuals. Do they represent a multitude of species? That would be the branching diagram that you see below. Or do they just represent variation within a population, or even better, within a deme, which means the local reproducing population? And of course, you can go either direction, and either of the directions has some real difficulties in terms of overshoot. So you can get into many ghost species, and on the other hand, you can get into container species. So the famous trash bag Homo erectus caricature versus all the, in my view, caricatures like Homo rudolfensis and so on, which are just represented by single fragmentary specimens. So let's ask a wise man what a species is. And if you read this, I mean, it's the 2nd chapter of The Origin of Species. Probably most modern paleoanthropologists will be shocked. Darwin basically says species don't exist. These are just labels at some level of hierarchy. And I think that's a very important insight. If you write a book about the origin of species, you basically deny that species exist in the old creationist sense that God created constant species. So the origin of species means species have an end and a start, and this end and start is kind of murky. So it's just a label. And what's most remarkable is his final statement that actually everything blends into variation between individuals. And I will come back to that aspect at the end of my presentation. So when we started analyzing Skull 5 in comparative context, we made a kind of a thought experiment. Think about the fossil record. Each of these blobs represents one fossil. So it's a pretty complete fossil record, which we actually don't have, but it's nice to play this thought experiment. There's only one axis of morphology. Of course, morphology is multidimensional, but just let's represent it by one axis. And of course, there's only one axis of time, which has a clear direction. Now, if we look at these fossils, there are 2 extreme ways of interpreting them. One is the classical species-driven interpretation, where we think about species appearing and disappearing, remaining more or less constant over their evolutionary lifetime, and clearly separated from each other. But there is actually no single argument that would hinder us of interpreting the very same fossil record in a completely different way, something like that. Where you actually look at ensembles of specimens representing populations or demes, in the best case paleodemes, which means fossil ensembles that potentially represent the same reproductive group of people or of individuals. And you see here we have a different kind of continuity than what we have here. Now, if we go to Dmanisi, we have the ideal preconditions to study which of the two views is more likely to be represented in the sample. Many people mistook our arguments and they say, okay, they just say it's at one spot and at one time, so it must be one species. That's not the case. It's just a precondition to test the hypothesis that's one population. So the question is, should we, let's say, group Dmanisi into 2 or 3 species, or just look at this interpretation where everything represents one thing, one unit with a lot of variation? And the only way to discriminate between the 2 hypotheses is basically looking at comparative actualistic data. That's the best thing we have. You go to museums, you look at labeled specimens, you know where they come from, and you start measuring variation. And here you just see 2 random modern humans, 2 random male chimps, and 2 random Dmanisi specimens. And now the question is, the variation that we see in Dmanisi, is it comparable to what we see in a modern chimpanzee population? Now, let's say in the first second when you look at this slide, everything looks like, well, it's the same thing, it's just chimpanzees. And the longer you look at it and try to find out what's a male and what's a female, and what's the difference between these skulls, you see all kinds of amazing differences. Sagittal crests, small faces, big faces, oblong faces, kind of shortened faces. So it's just amazing how much variation you have in one given population. All these specimens have been wild shot within a period of about 2 to 3 years. Most of them are from the Royal Museum, Royal Africa Museum in Belgium. So the question is this the same kind of variation? And the approach that we chose is basically a 2-pronged approach. The first is looking at the classical non-metric features. I will come back to that later. But what's probably more interesting for you is the geometric morphometric approach, where we just look at overall cranial shape. And the interesting thing is, if we analyze now variation in these different populations of chimps, bonobos, so 3 subspecies of chimps, different continental groups of humans, and the fossils that we just put in as single points, so there's no precondition of the analysis, no ordering according to categories like species or subspecies, this is what we get. And you see there's several patterns of variation that we can find out in these first 2 shape components, which explain only about 50% of the total variation. So if we look at this kind of variation that you see here, let's say from chimps to modern humans, of course that's not an evolutionary line, it's just a pattern of variation. You see, basically, it's about relative sizes of the brain case relative to the face. Something that most anthropologists will recognize. So here you just see the transformation of a chimp into a human, and you see it's a very complex, coordinated pattern of shape transformation. Of course, it's not a real transformation, but it's just the pattern. So what we can actually see here is the basic pattern of variation within these groups is kind of the same thing. And if we look at the width of variation, our result is that the kind of 3D shape variation of these crania in Dmanisi is fully compatible with the idea of a single population of a single species. Now, how did we get these results? Philip briefly mentioned the idea of resampling. So the idea is the following. Here is Dmanisi, 5 specimens, and you have a much bigger sample of chimps, for example. So we have to be on the safe side. We just measure them. We take out 5 specimens of chimps, just to match the 5 specimens of Dmanisi, and we calculate the maximum distance between those 5 specimens in shape space. So the most disparate morphologies. And we measure these. We do the same in Dmanisi. We measure it for a second, 5 specimen sample, and so on and so forth, 1,000 times. And then we compare the maximum distance that we find in Dmanisi, which is actually the one between the old adult, skull 5, and the juvenile, and compare it to what we find in chimps or in humans. And you see, of course, variation is considerable in Dmanisi, but it's by no means bigger than what you expect from a 5-specimen sample of a chimp population. So in our view, that's a very strong support for the Paleo-Deme hypothesis. And now, of course, this was kind of shocking news for all the people that spent their whole lives defining new Homo species, and we just lump everything into the same bag. And there has been heavy criticism. Fred Spoor wrote about big-mouthed and small-brained hominids, of course, probably meaning us. And in a recent paper by Mark Collard, you had these two very specific criticisms. The first is that we didn't actually look at the features that are normally used to discriminate between these African taxa, which is kind of a circular argument. The second one is interesting, that we couldn't even discriminate Neanderthals from skull 4, the one with the reduced face, the very old senile specimen. Well, the problem is today people spend their days announcing papers on Facebook and commenting them, but not reading. So the full information about all the non-metric characters is in the supplementary material that, of course, nobody reads. And probably also because it's kind of a grim reality. If you look at this table and try to find a pattern, it's just not there. Except you group specimens according to these features and then define them as species. But again, that's circular in the argument. Now, in the meantime, we have comparative data from hominoids, which analyze the same problem, and we hopefully publish those soon. Second aspect, we cannot discriminate between Neanderthals and Dmanisi. That's a problem that people don't understand the methods, or they don't take the time to try to understand the methods. Of course, if we present 2 dimensions of a multivariate space, this doesn't mean that because, let's say, look at the shadows of my hands, that's the Neanderthal, that's Homo erectus. If I project them in this way, they overlap. But still, these are 2 hands, so it depends from where you look at. Now, if you do a cluster analysis, you see that modern humans and Neanderthals are very different from Homo erectus and great apes. So there's a huge difference in shape. But we are not interested in that kind of difference. In the paper, we have been interested in variation that is common to all these taxa. So reading papers is sometimes worthwhile, but it takes some time. And so again, we can say we are on the safe side. Now let's get a little bit philosophical. What are the basic questions about early Homo? Of course, the first is how many species? We don't pretend to say everything is one species, but we have laid out the ways of how you can test it. What's the out of Africa signature of Homo erectus? Yesterday we have heard about Asian Homo erectus, which is quite different from what we see in Dmanisi and in Africa. And the last one, what can we learn from Dmanisi? Numbers of species. One or more. If you look at the African record, it's variable. Unfortunately, most of these specimens represent single finds lost in time and space, so it's very difficult to say. We cannot test directly these population-based hypotheses, but Fred Spoor and colleagues set out and basically applied the same kind of methodology for mandibular shape of OH7 and Homo erectus specimens. And their analysis, I think, supports the claim for two species in Africa, Homo habilis and Homo erectus, because there is a lot of variation that basically doesn't fit into what we know from modern humans. Great, so probably you have two species in Africa, but what's also interesting is that if you look closer at their data, it's a nice proof of a ghost species. So Homo rudolfensis turns out to be just one of those ghosts in the machine, in the analytical machine. Of course, Fred Spoor cannot give up the idea of rudolfensis, but the data are here. Second question, out of Africa signals. I mean, you know it from modern humans. You read it in newspapers. The farther away from Africa, variation of populations is reduced, a loss of diversity when you move out of Africa, changes in morphology. How is that in Homo erectus? Well, this is the general picture we have. The most uniform group is in East Asia, Southeast Asia, and then Dmanisi is more variable, and Africa is even more variable. Is this true? Not actually. If you look at the real numbers that we have for modern humans, you see that the loss of diversity is only about 10% from Africa to Java. It's not much, and it's probably not even noticeable in small samples. So we would expect much more diversity in Javanese Homo erectus than is currently acknowledged. And many of the so-called Pithecanthropus dubius specimens might just be the range of variation of Homo erectus in East Asia, considering that we expect about the same amount of variation as in Dmanisi and as in Africa. Third question, what can we learn from Dmanisi? In our view, over those many years that we have worked on the Dmanisi specimens and the meaning of variation, it's three things. We have to understand what time means, what space means, and what population biology means in order to understand human evolution. I come back to the diagram that I presented you at the outset. Between species or within species variation. Now, if we look at what this means in terms of time, if we speak about within species variation, it's a very brief amount of time, several tens or probably hundreds of generations, let's say back from our times to the Romans. Of course, we see a little bit of evolution happening, but mostly we speak about continuing populations. If we argue on the between species level, then we have to think about thousands of generations. And now you see the big difference between these schemes of arguments. Here we look at the source of evolution, and here we look at the result of evolution. And these are two completely different things. So if we assume the first perspective, we cannot say this is primitive and this is derived. It's just not possible, because otherwise we are God and can predict evolution. So I cannot say you are more primitive than Monsieur de Lumley. It's the same time and the same population. And this is very important to realize. We anthropologists are so accustomed to say this looks more primitive than that, and we automatically assume the second perspective. We should brainwash ourselves and just think about variation in terms of variation and not in terms of primitive derived. Now, what kind of methods can we use? Of course, that's the classical way of doing it, cladistics, and that's the more modern way to do it. Now I divert a little bit into the KT boundary. You know, you have these catastrophic events that lead to species reduction. In paleoanthropology, you also have catastrophic events. You know what? Cladistics. It's probably the single most pernicious event that happened to paleoanthropology. Cladistics was developed for the study of the morphology of thousands of species of holometabolous insects. Willy Hennig. So a typical catastrophe leads to extinction, and cladistics leads to overspeciation in some way. Now, what's the problem with cladistics? It's circular in its argument. That's the big problem. I don't need to read these out, but you see the basic problems that are not recognized. What's probably more important is the consequence. We cannot use cladistics to argue about speciosity and species diversity because these arguments are built in the start of the analysis. So it's the famous GIGO analysis, no giga, which means garbage in, garbage out. Actually, it's an official term in genetic cladistics, so there's no bad meaning on it. Now, just some digression again. Species recognition will remain a problem. So we have these extinct species. And there are some species where we actually hope that they will not get real Homo Erectus. So hopefully we will not see Homo Erectus next year, but just remain with Homo Erectus. And coming back to something more serious, I told you that I will come back to the citation of Darwin at the end of my talk. So Darwin says we have to look at individual differences. We don't yet know how to do it in terms of methodology and statistics. The geneticists today have exactly the same problem. They use cladistic methods, basically, and the whole argument is based on populations, but nobody knows what the population is. So we are kind of in a situation where we need some change in terms of methodology and in terms of how to approach variation. And with that statement, I close my talk. Thank you for your attention.
There are some questions? Oh, please.
What's the relationship between species and statistics? You said once statistics come, you get more species.
Actually, it's very simple. So what you do in cladistics, you define so-called operational taxonomic units. So you try to define something that